Okay, let's start. So today we're going to have sort of a quick overview of some aspects of logic. I can't hear anything because of these. I think these things have noise cancellation. It's kind of weird. No, now it's turned on. Now it's awareness. Okay, I can't really hear myself. Anyhow, so today we're going to have a quick overview of logic, some basics of logic, because because the course is called Logic in Computer Science, that would be a good reason, but also because a lot of the projects that you will be working on will be related to logic, and even the ones that are not related to logic are going to have elements of logic. So this is generally a good idea. Now, normally mathematicians think of logic as the foundation of mathematics. And if you have the attitude that logic and set theory provide the foundation of mathematics, then it will be only natural to think that you only need one foundation, right? Because you wouldn't build 3 foundations and then one math on top. That doesn't work. But in computer science, logic has a different role. It's a tool. It's an engineering tool that helps you solve problems. And it's very versatile. It's not one tool, it's a versatile set of tools. So the attitude that we take in computer science is that we can solve problems with logics. And we're not interested in what is the one true logic, but more like what kinds of logics can we usefully apply to problems. So you may entertain yourself by clicking here on this many different kinds of logic just to see that really there are different kinds of logic. This is the search result. Not all of them are about computer science, but many are. And so this is a wide area that we're not even going to attempt to give an overview. What I'm going to do instead is give you a more formal lecture about propositional and predicate logics so that you can then more easily understand how this is used in computer science and apply it in your project. So at the very basic, keep in mind that all I'm saying today is about a small fragment of logic, of possible kinds of logic, and that there are many others. Okay, but we don't have the time to go through all of that. I will say maybe a couple of sentences about what all the other ones are. But today we're going to look at propositional logic, which is the stuff that you get when you have the constants true and false and the basic logical connectives, and predicate logic, which is what you get when you add predicates and relations and the quantifiers for all that exists. Now, when you give a formal definition of what a logic is, there are several ways to do it. And here's 3 of them, which are the most common ones if you open a book on logic. One is called the Hilbert System. You can click on all these things and make an infinite descent into Wikipedia about this stuff. But briefly, the Hilbert systems they're the oldest. And there you put down a bunch of axioms, and then a proof is seen as a sequence of statements, and each statement is either an axiom or it follows from the previous statements. You may think that that's how human proofs are written, but that's not true. Human proofs are much closer to natural deduction, which is the second kind, where we have rules for deriving things, and the proof is actually a tree. And that's what we're going to do today. It's true that proofs written in the natural language are written sequentially because that's how language is written. But if you inspect the structure of a typical proof that you take out of a book, if it's written carefully, you will see that it has cases and subcases and subproofs, and that they form a tree. Then there is a related thing called the sequent calculus, which at first sight looks kind of like natural deduction, and it's quite similar. And also it has proofs take the form of trees, but it also has important differences from natural deduction. It builds in a symmetry that automatically gives you classical logic, at least the basic kind of sequence calculus. When you study it, it really is different from natural deduction. But I'm mentioning it because it's also important. So we will be looking at the natural deduction style, which is also related to type theory, as we shall see next week. Now, what other kinds of logic are there, apart from predicate logic? Well, actually, this predicate logic, it's also sometimes called first-order logic. So one thing that can happen is that you can have higher orders, but that doesn't really take you out of the realm of predicate logic. It's just that you have higher order predicates. But then there are other things like modal logics. In modal logics, you have the so-called modal operators. One of them is like this box, where you say box phi. And this can mean various things. It can mean something like phi is not only true now, but it will be true in all states that we can ever reach in the future. And this kind of thing is useful in computer science for describing properties of transition systems, where you make a statement about the system. You have some configuration, and you know that actions will be taken and the system will change, and you want to say it's always going to be the case that something holds. It's not just accidental. Or maybe you want to say it's possible that we will reach such and such state. That's a different modal operator. It's called the diamond. Modal logic also has applications outside of computer science. Of course, it was invented outside of computer. It was invented by philosophers, logicians, Kripke. Maybe it wasn't Kripke. Kripke was very important, but I don't know if he invented it. So, for instance, box phi might mean we know something is to know that phi is true, as opposed to just phi. So, if you just state phi, that just means that phi is true. But if you say box phi, that means I know it's true, because there is a difference between truth and knowledge, right? And then you can have things like the statement that box phi implies phi. That means knowledge is never false, because it says if I know something, then it's actually true. And you can then think about what laws you get. So this is an interesting topic. Linear logic is a logic where you are very careful about how you use your hypotheses. So you have to use each hypothesis exactly once. You can't use it several times. And this leads to a logic which computer scientists say it's resource aware, because the way that you use hypotheses or variables more generally tells you how you're accessing resources in general. And so this is the sort of logic that has applications in theoretical computer science. Then of course there are things like temporal logic, where you want to speak about time, saying things like this condition will be true so far as the other condition is true, or whenever this condition becomes false, then something happens, things like that. And this again is obviously going to be useful for systems in computer science that where you need to express properties in time. And these are not things that you can easily do in just ordinary logic. I mean, you can probably encode them, but it's really cumbersome and unnecessary, and it's a bad idea to do so. It's better to just use a custom logic that solves your problem directly, if you can. Okay, so let's have a look at propositional logic. You will recall that we already. I wonder if this works. Yeah, it seems to work. We already spoke about. No, it doesn't. This is my Jupyter linking. Doesn't work. We already spoke about inference rules, which we used to give rules of inductive generation, where you inductively generate the elements of the natural numbers, and we inductively generated things like the less than or equal relation. You will remember those things. So in general, just to remind you, we had inference rules that looked like this. You had a bunch of premises, and then you had a conclusion. And the way that you read this is that if if all these premises have been established, then you can also conclude that C holds. Now, the P's and the C's here, the P's and the C's, are usually some sort of assertions. So, for instance, they were the assertions like 0 is a natural number. And in general, we say that they are judgments. So together, these things are called judgments. And they can express various kinds of information, but this information is always about something being the case or something having been constructed according to some rules or something like that. So in the propositional calculus or propositional logic, what we have is, let's first describe what the formulas are. So first we have formulas. And we assume that there is a set of atomic formulas. So these are just some symbols that appear that we want, that maybe we use for modeling our system, whatever it is. And then we have the two constants, true and false, false and true. And then we have connectives. So the connectives are used to generate other formulas. And we'll have conjunction, disjunction, and implication. And with these, you can then build all your, so these are just some symbols, P, Q, R. With these, you can build the formulas, and you build them inductively, of course. Now, there are two abbreviations that we will use, which is that this one, phi is equivalent to psi, is an abbreviation for phi and psi. Nope. Phi implies psi, and psi implies phi. And then the negation of phi is an abbreviation for phi implies false. Okay, so let's have a look at this much in Agda. Of course, I'm going to now also, one of the points that I'm doing here is I'm going to formalize this logic inside Agda. And many of you in your projects will be doing something similar. You will be taking either a logic or a small programming language, and you will need to formalize it. And the steps will be very similar to what I'm doing. The first step will be to describe the expressions that you can use in your programming language or the formulas that you can build. And this is precisely what I'm doing now. I'm first describing the syntax. Okay, so here we are. How are we going to set this up? We're going to have a module called Propositional Logic, and it takes a set of atomic formulas as a parameter. Now, what this is would depend on what you're doing. If you are a logic textbook, you would just have, for each natural number n, you would have an atomic formula p sub n, because the only thing you care about is that you never run out of them. But if you're modeling a computer system, then you would have some basic statements about your system, like the red light is on, the switch is on, something, the system is over here, it's over there, some basic statements, and then you would discuss which ones are true and which ones are false. And you would invent symbols for these statements. Okay, so this is just some basic concrete syntax here. And of course, the formulas now, since they are an inductively generated data type, are written down here. And so, for instance, conjunction is a binary operation, so formula to formula goes to formula. Atomic formulas, when written, will be written like this, like with a back quote. But we'll never actually, because we're not going to apply this today to any specific example, we'll never actually see an atomic formula, because we'll always be inside this module. We'll just be doing the generalities. We're not applying this today. Okay, here are the two abbreviations. Now we come to the judgment form. As I said, you always have to decide what these P's and C's in your inference rules are. And we already saw that they can be typing judgments, saying something has a type. Now, the judgment form of propositional logic is, they're called hypothetical judgments. And it's written like this. You have a bunch of formulas, and then you write a V dash like that, and then you write a formula. These guys here are called hypotheses. And this is, again, usually called the conclusion. And this looks quite similar to what I wrote up here, right? I mean, an inference rule also looks kind of like this, which is, again, you might be wondering, but isn't this the same as saying that? Right? And actually, why are we even bothering with this? Because we could just maybe write this. And I think every student of logic at some point asks, why do you have so many ways of saying mostly what amounts to implication? Right? Because the way you read this is the hypotheses phi 1 to phi n entail, I'll use the word entail, psi. So here it was from the premises, from the premises we get the conclusion. Right? And here we have the conjunction of these implies psi. It's true that they're all similar, but they live at different levels. They live in different worlds. A rule of inference is something that describes a logic. It tells you how to use a logic. Okay? It doesn't tell you anything about what's true out there. It is purely about, or what is true about a mathematical structure. It's telling you how to construct a certain object. And this thing here, a hypothetical judgment, now this is what we actually care about. Let me try to color this a little bit. This is an entity that is inside the logic. This is part of the logic itself. One way of saying this is to say that an inference rule lives at the this is at the meta level, because the things that I am doing as an observer of the logic are the meta level, and this thing here is something that holds about. This is a relationship between propositions that the logic can establish. So it's different from the rule. And then this one, the third one, this one is internal, or we also say it's object level, or internal to logic. So at this point, I would just like to acknowledge the fact that these three things look similar and that it's worthwhile discussing them. But I think it's also important to first work with them a little bit and then maybe come back later to say, okay, so let's now see what the differences were. Okay, so this is called a hypothetical judgment because it's capturing the idea, something that mathematicians are very good at, namely reasoning under hypotheses. This is something that takes training, and mathematicians know how to do it, but ordinary people get easily confused. So in mathematics, we are used to assuming a hypothesis, even though we don't know whether it's true or false, or maybe we even believe that it is false. For instance, you say, assume we have two, you can say something crazy like, assume we have a triangle whose sum of angles does not add up to 180 degrees. Then something, something, something. So you might assume something that you know is false, but that's not going to throw you off. You will still be able to perform valid reasoning. And the hypothetical judgments are about that kind of reasoning, when you're reasoning with some hypotheses in mind. If you think about this in real life, you will see that hypothetical reasoning in real life doesn't work so well. You cannot go, you come home today, it's not raining, and you come home and the first thing you say is, suppose it were raining now. It will be impossible to continue the discussion with your family members unless they are mathematicians, right? Because they will say, you will immediately say, but it's not raining. And then you'll say, but suppose it were raining, but it's not raining. What is your point? It'll just stop right there, okay? So that's why the word hypothetical here is important. These are hypothetical judgments, reasoning with hypotheses. Okay. And the point is that this thing here is keeping track of what are the current hypotheses. Because during an argument, when you're making a logical argument, the set of hypotheses that are currently valid at any one moment, it changes. So you may temporarily maybe assume an additional hypothesis and do something, and then you discharge it and you don't have it anymore, and so on. Okay, now come the rules. So the rules are going to be, well, they're not going to be like this. They're going to have such hypotheses as premises and conclusions. So let's have a look at some of them. And in general, when you have a logic, there will be so many, at least in natural deduction style, you always follow a certain pattern. There are structural rules. Structural rules are rules that apply, they typically apply in many situations, they're not about one particular connective. They're about general stuff. Then the connectives, at least in natural deduction, typically come with two kinds of rules. The introduction rules, which tell you how do you prove a connective, and the elimination rules, which tell you how do I use a connective. There might be some other special rules, like excluded middle, and that are not easily classified as anything. And then usually when you have those, that means that your logic is probably doing something rather special and is maybe, creeping out of this beautiful picture of natural deduction that you get if you have only nice introduction and elimination rules. Okay, so now here, when I wrote this, the hypotheses, it looks like this is a list of hypotheses. But in a mathematical argument, the stuff that you're currently assuming is not really ordered. For instance, if I say assume x is greater than 0 and assume that y is greater than, 7, it doesn't matter if I reorder them, at least not when they're independent of each other. And also assuming the same thing twice doesn't really get you anything, right? Assume that x is greater than 0, then again assume that x is greater than 0, you're going to wonder, why am I saying this? Now, in formal logic, you have to pay attention to such details. So one way to understand hypotheses is that it's a set of hypotheses, because that would make sense. The order is not important, and it doesn't matter how many times a hypothesis appears. But if you're very formal about it, you will say, well, sets, I feel a bit uneasy about them. So how about if they were lists? Because lists are inductively generated, this is nice syntax, everything will be super clear. So we're going to say that hypotheses are lists. But then our structural rules will say that these lists are actually representations of finite sets. That's what we want to say. So here are some first sets of structural rules. Oh, by the way, we will also need one thing that happens is that given a statement, you need to be able to tell whether it is one of the hypotheses. You have to be able to recognize that something is a hypothesis in Agda, but that's just the element hood in the list, and we have done element hood in the list, so I just copied it here. So how do you say that something is an element of the list? Well, there are two possibilities. X is an element of the list that starts with X, or X is an element of the list that starts with Y, provided that X is an element of the rest of the list. Notice the double curly braces here. This is Agda technology, which says this is what is called an instance argument, and it tells Agda that it can automatically derive it from things that are tagged as instances, and these two are tagged as instances. So the practical effect of this is that with a bit of luck, I don't have to explain to Agda why something is why a given hypothesis, why a given formula is a hypothesis. It'll try to reconstruct the proof by itself. We'll come to it, you'll see. But the only thing to remember right now is that this means it's an element of a list. Okay, so how do you formalize this here? Well, actually what we're going to formalize is, if you think about it, what we're doing is this thing here is something that takes a list of hypotheses and the formula, right? And as a type, it's similar. The way that we should think about it is when you have a judgment, you think of it as a type whose elements are all the ways of deriving that judgment. So this is going to be an inductive data type that tells us how to derive judgments. So let's have a look. So we're going to say, okay, my judgment, and this is going to always be the case whenever you have a formal system, your judgments, whatever they are, so they might not be hypothetical judgments. They might be some statements about programs or in a programming language, for instance. So what we're going to say is hypothesis delta entail phi, and then we'll give rules. Okay, so let's read these rules. The first rule is called the rule of weakening, and it says, well, given any hypothesis, delta 1 and delta 2, and any formula find psi, suppose that you can derive psi from these hypotheses. Then you can also derive it from these hypotheses. Okay, so this just says it's always safe to assume more. You can if you assume another hypothesis, nothing will break. That's why it's called weakening, because it weakens the thing that you proved. The more you assume, the easier it is to prove, therefore you weakened it. Contraction says that if you have an assumption that appears twice, then you can delete one of the copies. We don't need double assumptions. Okay? And exchange says you can exchange the order of hypotheses. So these two together are saying the lists of hypotheses are actually encoding finite sets, because you can reorder them, order is not important, and you can remove duplicates. It doesn't matter how many times it appears. There are systems. So we took these as basic rules, but later we will see that some of these we will discuss whether they are really necessary. So those are the structured rules.
Sorry, doesn't this work only if the same hypothesis is assumed adjacently?
Yes. So the question is, we can only remove adjacent copies. Okay, but now you look at the next rule and tell me how you would remove non-adjacent copies. Yeah. So if you have two copies that are far apart, you use a bunch of exchanges to bring them together, and then you contract them. Okay.
Also,
yes.
Question: why did we define this by nesting these two arguments in between the delta 1 and delta 2?
As opposed to?
At the beginning, let's say.
Okay. So the question is, why didn't we do it for the two phis just appearing at the beginning?
Yeah.
Okay. For this part, it wouldn't matter, because exchange would always allow you to bring them up to the front.
But exchange is also defined in the middle.
Yeah, okay, so let's see. If you overdo it, it's going to be weird, okay? So I think you have to allow exchange everywhere so that you can move things around. But once you have allowed exchange everywhere, then you could only say, I will only contract copies at the beginning or at the end.
Okay.
But for convenience, it's written like this, and also so that it's easier to understand that you can write that this is about saying that the lists really represent sets. Of course, you could also ask, how about a contraction that has a delta 3 in the middle, right? That would be more general, and you could do that as well. So when you have these alternative rules that you think of, okay, so then the important thing is, does it make a difference? So for instance, if I add some other form of contraction, it doesn't make a difference. And these rules because the rule that I'm thinking of, I could get it from the existing rules. This is a bit about how vector bases generate vector spaces. You know, you can have different bases for a vector space, but they will generate the same base. They'll have the same linear span. So here we are discussing what are our basic building blocks, and different sets would still give me exactly the same set of derivable hypothetical judgments. And there is, of course, this is an important design question, and doing it well is important. Because if you design it well, it'll have nice properties. The one that I'm showing you here is not designed well. It's written this way for educational purposes to explain contraction and exchange. But really for the sort of meta-theoretical study, I wouldn't want to have these. I would want to show later that I can get them anyway. Because it's good to have a small set of rules, not a large set of rules. Okay. Now, the next one is called hypotheses, the hypothesis rule, and it says that delta entails phi if phi appears in delta. So every hypothesis entails itself. Yes? This is also structural. It's a special rule. It's not about the connective, so sometimes people say it's structural. Okay, then we have the rules for true and false. And these are a bit special because true has only an introduction rule, but false only has an elimination rule. Let's read them. If you have any hypothesis delta, well, then without any premises. See, maybe just to be clear, how would I write this on paper? Okay, so this on paper would look, or maybe let's write this one on paper. This one on paper, let's assume this is paper, okay, would be like this. People would write this. Okay, just this. They wouldn't write this. This doesn't make any sense. Okay? It doesn't make any sense. If anything, if you want to explain what this delta is, you have to say for all lists delta of hypotheses, we have such a rule, which is this business here. Yes? So don't confuse the fact that in Agda we are saying what the type of delta is with the fact that we might have a premise. See? So the next rule makes this clear. It says, given any set of hypotheses delta, or any lists of hypotheses, and any formula phi, if you can prove this premise, so writing this rule now will be like this. If you can derive false, then you can derive phi. From false, anything follows. Yep. Okay. Now let's look at the rule that has actually proper introduction and elimination rules. How do you prove phi and psi? To prove phi and psi, you prove, well, separately phi and separately psi. This is written in a vertical way. In a logic textbook, it's going to be written, again, it's going to be written like this. Right. I'm just telling you how to read the rules. All this says is to prove a conjunction, you prove each one of them. how do you use a conjunction? Well, if you have already derived phi and psi, then you can forget the psi and you just keep the phi. Or you can just keep the psi. So there are two elimination rules, the first one and the second one, or the left one and the right one, which extract the components, the conjuncts. How about, yes? Say again? Oh, thank you. Yes. Thanks. How about disjunction? Disjunction is a bit similar, and we also have here, it's dual. So it has two introduction rules. If I've derived phi, then I can also derive phi or psi. And if I derive psi, I can also derive phi and psi, or psi. So there are two of them. These are the direct ways of proving a disjunction. And let's look at the elimination. So I'll write the elimination on paper again, because it's easier to read. What does it say? It says, so elimination, you should always think of it like this. Okay, so suppose I have proved a disjunction. How can I use this? What do I do? What's this good for? So if you want, so if I tell you something like, x is greater than 5, or it's negative, and then you want to do something, you will say, well, okay, but there are two cases. If x is greater than 5, then that's one case, and if x is negative, that's the other case. So this is about doing two cases. So you say, okay, we consider two cases. One is when phi holds, and then we prove something. Which letter did we use here? Oh, phi 1, phi 2. Okay, I'll just use the third letter, theta. So, and if psi holds, I can do theta. The way you read this is, I can do in either case. So I know one of these cases is going to hold, but in either case, I can derive theta. Then I can derive theta. Right? Because from these deltas, I can first get the or, and then no matter which of these two I got, I will be able to get theta from one of them, or maybe even both of them. It doesn't matter. This is now an example where I temporarily have a new hypothesis. I'm now reasoning hypothetically under the assumption that phi is the case that holds, and then here psi. Questions? No? Okay. The implication is, I think, is less mysterious. How do you prove an implication? Phi implies psi. Well, you assume psi. Well, you assume phi. So you put it among the hypotheses, and then you get the conclusion. You have to prove the proof psi, the consequent. How do you use an implication? Again, the thing that you ask yourself is, for elimination rule, the thing that you ask yourself is to say, okay, so suppose somebody hands me an implication. What can I do? What's some good use for it? But you see, you do this all the time in math. Usually these implications that you are handed are called theorems and lemmas that somebody else proved a long time ago, that say things like, if, I don't know, if p is a prime number and p squared divides n, then la 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 la. So that's something like, that's an implication. Then you say, oh, if I want to use that, I need to show that p is a prime number. So what you do is, if you show that phi holds, you will be able to conclude that psi holds. And this is the rule, which is then written here. From phi implies psi, and phi we may conclude psi. Okay, so these are the rules written in mathematical notation. Okay, so how do we do this now? How do we do this in Agda? So in Agda, you will practice this in the exercises. Here is one of these things here is one of these rules. Here is an example derivation. So what happens now is somebody gives you a statement and you want to derive it. So in order to derive it, you have to say, how do I use these rules to construct the statement? And you will do this in the exercises. But if we try to do this a little bit on paper, let's see. How would it go? So I'll do just half of it. Suppose I want to show suppose I want to show, which one should we do? The other one is more interesting. Okay, suppose I want to do this, that if A implies B, nope, it should be the same as in the notes. If A implies C and B implies C, then A or B implies C. Okay, so the way I want to show you one derivation tree so that you have it in front of your eyes, and this derivation tree is going to be like 1/2 of this derivation tree here, because this one is actually proving the equivalence, and we will just do one side. Okay, so what do you do? Well, it's an implication. So how do we prove an implication? We use implication intro, which means we put this thing in the, we take this thing, we assume it, and then we have to derive this. But this is an implication. So I do another intro, and I put this one among the hypotheses. Okay? Now I'm stuck. Now I just am staring at C. I can't use an introduction rule. I have to use an elimination rule, but which one? Well, I could use the elimination rule for and, maybe, or I have to do something with one of the hypotheses. Do you have any ideas what to do? Yes, so we want to consider two cases. Because we see that we assumed A or B, we want to consider two cases, namely what happens if A holds and what happens if, so we're going to use conjunction elimination. And the first, well, which conjunction is it going to be? It's going to be A or B. So first, I am actually going to painstakingly write out everything here, just to see that this is a horrible thing to do by hand. So my first task is to show this. Well, but this is a hypothesis. Okay? Then it is going to get painful. Let me introduce an abbreviation, namely that this thing here, okay, this much, I will call this delta. Okay, so now I can proceed. So then I have what happens if A holds and I need to prove C, and what happens if B holds and I need to prove C. Okay? So I go here. Now it looks a bit weird, but remember delta is just this thing here. How am I going to get C? Sorry? Which one?
So what you want to get is...
Okay, let's do this one because it's going to be easier. It'll grow up here. And then this one I will just say similar. Okay? I'm not going to draw it. So how do you get C? What I have is I have A implies C and B implies C, A or B, and B. Another disjunction elimination is very unlikely that if I do the same disjunction elimination again that I'll get anywhere. Yeah, it's going to be an implication elimination because it'll say that, well, how? I need a longer line. What are the two things that I'm going to prove? I'm going to prove that from which one? From B implies C and B, I can get C. You see? If I manage to prove B implies C and B, I will get C. So that is the junction elimination. Okay, can I get this one? Yes, that's a hypothesis. It's already a hypothesis. How about this one? Where will I get B implies C? Remember what delta is. It's in here, see? It's in here. So how can I get B implies C? It's and elim 2. Because I will say I can get it from A and from A implies C and B implies C. right? And then this one I can get from hypothesis. It's part of the hypothesis. And then here, it's similar, just that A and B exchange roles. That's what a derivation looks like. Okay. You're going to have fun writing this. Here is an example which, okay, this one I'll just quickly show you in Agda. This is commented out. Okay, so what does this example say? The example says if your assumptions are, here, it's this one, okay? So if my hypotheses are A, B, and C, and another A, and then I want to prove something, okay? It doesn't really matter what. The important thing is that there are two A's. So when you do this with Agda, okay, you come here and you say, what do you want me to prove? Oh, you want me to prove a conjunction? Sure, no problem. It's a conjunction introduction. And Agda says, okay, here you have to prove B. And I say, well, where will I get B from? Oh, I will get B from B and C. So that's going to be elimination, and it's going to be the first one because it's on the left. And then it says, okay, but what's this conjunction you're talking about? And I say, it's a hypothesis. It's a hypothesis that B and C holds. And then, oh, yes, and now because of these instance arguments, first of all, the whole doesn't want to work, which is super annoying. We've reached the limits of Agda here. No? Whoop, whoop. One more, okay. See, now it's happy, yeah? And what happened was that this hypothesis here, I told it that B and C appears in the list, and then it generated the evidence that it appears in the list. So now I'll try a very similar trick when I get here. I'll say, well, I need to prove A and top, so that's an AND introduction. And then this one here is, oh, you need to prove top. Well, that's top introduction, no problem there. Here, it says you need to prove A. And then I say, oh, this is horrible. The whole doesn't work. I have to say, okay, it's a hypothesis. And now Agda is unhappy. And the reason that it's unhappy is that it's trying to generate all proofs of this fact. You see? It's trying to generate the fact that A is an element of this list. But it can tell that there are two ways to establish that A is an element of this list because it appears twice. And so now it's telling me, oh, but I don't know which one you meant. There's two of them, la, 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 la. Okay? It's a minor annoyance that I want you to be aware of. And also, this shows that you definitely don't want to do this with your bare hands in Agda. There are ways to tell. You can actually tell here if you want to. You can be very explicit about which hypothesis you have in mind, because you can just instantiate it in double braces. And I say, here I say, oh, I meant the first copy of A. This is the first copy of A. And down here, I put down the second copy, which is in element, like it gets painful. Okay, we don't want to do this. But it's here so that you can see what's going on. Okay, I think now is a good time for stopping a little bit. And then we're going to look at the derivable and admissible rules. So meet you at 15:23-ish.